Thank you very much. So welcome to the weather briefing today. I am Yasmin Markl, my colleague is Andreas Wirth. We are both working for the Austrian Institute for Meteorology and Geodynamics, that's ZAMG. Andreas is in Vienna and I have my office in Salzburg. So to begin this weather briefing with, I would like to make a quick warm-up. You have on the top of your screen, I think, the annotation tools, and you can test them now. Okay, here's the arrow. So yeah, I would like to actually, I would like you to pick one of the icons and put a cross there or your name or whatever you like. I will maybe do the first. And now, because it's Friday afternoon and I don't want you to fall asleep within the next half hour, I would like that we do this exercise 5 times together. So I will count and everybody gets up and just quickly get alive a little bit. So 1, 2, 3, 4, 5. Well done. All right, so Michaela and Robert have to show me one day how it goes with this very fancy exercise. Thanks a lot for that. I feel much better now. I feel much warmer now, and this is so important after this really cold spring. I don't know how it was for you, but here in Austria we had a really cold, cool, and wet spring. I would like to show some statistics about that now. So let's move on. Okay, apparently it shows, everything at the same time. I actually was planning to make some animation here, but this is not working. Maybe I should switch to share my screen instead, because otherwise I'm spoiling some of my things. Just 1 second, I can quickly switch here. I'm sorry for that. Share my desktop should be in a second. I think we are already there. Okay, starting from the beginning. We have done that. Okay, back to the statistics for Austria. So this was January and February, the mean temperature. And we see that January was a little bit too cold in the west and a little bit warmer in the east, but February, wow, was really warm. It was more or less the spring of this year, because if you look at March, this was more or less the average compared to the long-term mean, but April was much cooler, and May, at least until now, was about 1.9 degrees cooler than the long-term temperature for May. And yeah, I think the last days of May will not change this. If we look at the global and especially at the European temperature anomaly for March, we have a very similar picture. Here we see especially that the south of Europe experienced a cooler March, while the north was actually a bit warmer. But if we look at April for this year, we see that most parts of Europe just were really cool. Unfortunately, the chart for May is not yet out, because May has not finished yet, but you can check it out at the ECMWF website in a few days, how this looks for May. I guess it's probably pretty similar than here. This is the monthly European surface air temperature anomalies. So what we see here for Europe are the single months, and we see a general trend to warmer months. That is very obvious, and here in the very end we see this cold April and this little bit colder March. However, if we go to a global part, there hasn't been a too cold month since about, I don't know, 2014-15. So this is not surprising, but actually very shocking. Yeah. So here we see where the journey goes. Okay, now the big question is, when will the summer come? Where is it finally? Before we come to that, I would like to start with the current weather situation with this water vapor image. And so, yeah, this is from today in the morning, 9 UTC. And I have a little task for you. I want you to have the air mass RGB in mind. And if you are a little experienced, to find the areas where you would expect a white or very bright color if you look at the air mass RGB. So if you think about the air mass RGB, okay, so. Okay, so areas with bright color in air mass RGB. Okay, in the meantime, you have put really good guesses here. Thank you. Yeah. I will. Oh, sorry. Yeah, but I will move on anyway. Okay. Difficult handling here. Why is it? Okay, I have to close the notice. Now we can move on. Okay. When is it white color actually? It is when all contributions from all color beams are more or less the same. So we have white color if red, green and blue have a similar value, and this is the case for high opaque clouds. And why is this the case? Because red is high because of the brightness temperature difference. Is actually small, then red gets a high color. We have a high contribution also of green because of high cloud top, and blue actually we have a small contribution from the water vapor 6.2 channel because the radiation that is measured is small, but this is an inverted channel, so we have also a high signal of blue, and this is why the result is a very bright color. I will show you in a bit. The next exercise is to find reddish colors or brown colors that you might expect at the air mass RGB. So I hope you can again annotate. Okay, yeah. Should work now. Yes. Okay, this is not new to you. That's very nice to see. All right. Okay, thank you. Wow, you do not even want to stop drawing. That's nice. Okay, thanks a lot. Very good. And now let's have a quick look at that. Where do we have red areas? We have a high red contribution in the air mass RGB if we have a small brightness temperature difference, then we have large values of red. And this is the case when the difference between water vapor 6.2 and water vapor 7.3 is small. So if we have throughout this upper layer atmosphere a dry layer, and so automatically red or brownish color means dry air masses. And this, on the other hand, can be an indicator for subsiding air, for example. All right, let's look at the image, the air mass image that we have already built in our head. Here it is. Okay, and I have added some arrows that show different air masses, but as I have seen, you're quite familiar with this type of RGB. Well done. Now, what does this mean for the current weather? We have here this system out in the Atlantic with the occlusion here, and I guess there's a warm front and cold front here. I think there's even another occlusion, a very old system that lies somewhere here. Then this small system that brings clouds and changeable weather over Spain and southern France, and then we have here some kind of upper level low or older system, even here just trough and here another smaller system that bring changeable spring conditions, and in between those little systems there might be some high pressure developing here over France, Germany, the Netherlands. The next task is to have a look at this infrared image, 10.8 micrometers, and now I want you to think about the dust RGB and find thick, high and cold ice clouds. This is probably more difficult, more advanced. It's depicted in the dust RGB as red color. And okay, I will approve again. Yeah. Okay. All right. Thank you. Not bad. Yeah. As I said, this is really much more difficult to see, and I will not go with you through thick mid-level clouds or dust because it's almost impossible, in my opinion, to find it just by looking at this infrared image. I will, however, directly go to the solution. Okay, thank you for annotating. So that's the dust RGB, and yeah, you have very nicely identified the main thick cloud formations here. The red colors, well done, and then we have this yellow color that indicates thick mid-level clouds. There are actually many parts where we have them, and we also have some little area of dust here in the lower right corner. I think that's probably above Afghanistan. This pinkish color, this is dust in the atmosphere. Great, thanks. So now we can already have a look at the weather outlook, what is coming for the next days. This is for today, 12 UTC. We have geopotential, equivalent potential temperature, precipitation, and wind gusts. And we will quickly and roughly go over the next days. So as I have said here, some kind of ridge building up. The next frontal system is here in front of Iceland. And here this upper level low, or all the systems with this trough going down, reaching down to the Balkan. And when we go forward in time, we see that this low here cannot really decide. Actually, it doesn't want to go, doesn't want to stay. It somehow circulates around, and this ridge that is originally, or does also not really move, and remains here over Spain and France, and then this system splits apart. So we probably will remain in this changeable spring conditions, probably a little bit warmer air coming from the south, but we do not have this directly strong southerly flow that brings really warm summer air to the Alps or to Middle Europe, so that will probably be missing. So this is already Sunday noon now, probably remaining rather unstable. Every day we see some kind of precipitation over Europe, so not really summer weather coming to us as it looks like from today's view. What does ECMWF say? We are looking at the extended range forecast, the weekly anomaly for temperature and precipitation. So next week we still have this too cold temperature over most parts of Europe, but probably already warmer over Portugal and Spain. However, this colder area moves to the east in the week after, while this a little bit too warm area might develop further and then cover probably southern Europe. That's just a rough forecast, a very rough view in the future. I hope the best for the summer, and I hope it will come soon. And now I I will give the word to Andreas. Andreas, you can take over. If there are questions, I would be happy to take them in the very end. Thank you very much.
Thank you, Yasmin. I will do the same. I will share my screen. I'm a bit lost. What should I share? Yes. I will share my desktop first, and then I will open my PowerPoint. So I hope you can see it. Yes. Okay, I'm going to give a little extra to this weather briefing, and I have spent some time investigating the passage of a cold front along the Alps. And it's a situation that happened in the middle of May, from 10 to 12 May. Why do I want to show that? Just because I think that the models, or here especially the ECMWF model that I used from ePort or ePort Pro, depict very well the situation. And it's a good opportunity to show how good the models are already nowadays. So some of you may remember that I was talking about a flight from Vienna to Tenerife and last year, and that because of strong Foehn situation, there was some icing on the plane and it had to return to Vienna. The situation I'm going to talk about is very similar to the one from 3 October. We have a cold front that you can see here in the infrared image that comes from west to east, does not cross it. It goes along the eastern part of the Alps. And in fact, I'm not so much interested in the front. I'm more interested in the situation before the front arrives. And that's where we usually have the strong airflow crossing the Alps from south to north. And that is related to many interesting meteorological phenomena that I want to show now and that are very well reflected in the model fields. So this is the synoptic analysis of the surface front. You see the front that arrives. And there's a nice characteristic of this front. Of course, it crosses the Alps in the western part, but in the eastern part, it goes along the Alps. But in front of the Alps, you have the strong Foehn effect. You have the airstream from south to north. And this is what I'm going to look, what we are going to look closer. So what happens here, the front goes along the Alps. And what is interesting is that the north of the Alps, the front lags a little bit behind, while in the south, the front propagates from faster from west to east. And yeah, you see that the front is a little bit wave-like. There's a small warm front that happens over Germany, eastern Germany here, and the southern part of the front propagates much faster than the northern part. When we have airstream that crosses some mountain range, we have a very interesting effect that is related to the conservation of potential vorticity, and it makes that we see that the air is not crossing the Alps in a straight way, but undulates and deviates to the west and to the east, depending on the compression of the air column. Either it's stretched or it's compressed. If you have an air column that passes over the Alps, it influences strongly the relative vorticity. And this is an effect that is well known, also from the Alps, but also from the United States when it crosses the mountain range over there. And this effect, you can see it here in the relative stream, is very nicely represented in the 700 hectopascal streamlines. You see the deviation to the east when air comes from the south and is deviated over the Alps, and comes back to a more cyclonic vorticity, which deviates again to the left in the northern hemisphere, and this is really nicely shown in this model field. You can also see the barrage effects of the airstream. You see on the surface pressure a high pressure region, and in the north of the Alps you have a lower pressure region and a strong pressure gradient here along the Alps. This is very clearly seen in this model field, and yeah, depicts the situation very well. Connected to that, and that's what we had also on the 3 October, is lee cloudiness. Lee cloudiness are small ice crystals that can be seen here, depicted in black. If they are thin, small ice crystals, and this is a dust RGB. We have two types of lee cloudiness or wave developing at the lee side of mountains. We have either the trapped lee waves or we have the vertically propagating waves. And in this case here, we have clearly the vertically propagating waves. That means we have the Foehn effect in the lower layers, and we have upward raising air masses that forms typically thin cirrus clouds that can be seen either in the dust image or, as you can see in the next image here, this is the Severe Storms RGB, and you can see that yellow color with some greenish hue, and if the yellow is getting into or turning into the green, that means that there are some supercooled cloud droplets, which on their side again lead to icing on the airframe of aircraft, and that can be dangerous. And that is what happened on 3 October. But this situation is not so rare. You can often see that situation in the Alps, in the Alpine region. So let's come back to our model fields. I put a cross section from south to north, so from Italy to the Czech Republic. And what you can see here is the vertical motion. And you see the Foehn effect here, the descending air on the northern part of the Alps, very nicely depicted in the model fields, and the rising air here that forms the lee cloudiness. You can see the rising air in this region that forms here as depicted in this image from Comet. So the model fields depict that really nicely in this cross section. What you also can see is the Foehn effect that is mainly in the ground region. Again, here the descending air, and you would expect here on the northern part of the Alps warmer air masses. That is clearly seen here in the cross section. This is the temperature. You see an increase of the warm air up to higher levels compared to the southern part, where we still have warm air in mid of May, but not as warm as in the northern part. So while in the higher levels you don't see any difference between the northern part and the southern part, this is nearly the same temperature. The Foehn effect is clearly visible here in the lower levels of the atmosphere. So again, humidity, also very nicely depicted. That's what we expect. Quite dry air because of the descending relative humidity, dry air, and moist air, or air that is near saturation here in the layer where we have seen the ice shields. This is exactly in reality. These are prognostic fields, but they depict the physics very well and catch the actual situations extraordinarily well. Again, this is the same cross section, but this time with the temperature advection, and this is the field that attracted my attention and the attention of a colleague from the Air Weather Service, because we have here strong cold air advection. This is the region where we have the Foehn, the descending air, but you see that over a few hours that the temperature is decreasing and dramatically decreasing, and we were discussing how that can be. So that is the region where we have found strong cold air advection. In fact, there is the Foehn effect. So if we have an increasing Foehn situation, then there would be warm air advection. But in this case, we have over a longer period cold air advection. So this is the time loop, and you see that this cold air advection, it starts here. It's quite permanently over 6 hours the images are in a 6-hour lab. The last image is this one where the cold air advection disappears. But for many hours, even for a few days, this cold air advection persists. And we were discussing why this happens. And there are probably 2 reasons that came out, but maybe you can post in the chat why we have this strong Foehn, this strong cold air advection. The first explanation could be that the Foehn is weakening due to the approaching cold front, and the second, which seems of stronger probability of a higher effect, is that, as you have seen in the beginning, the southern part of the cold front propagates much faster than the northern part, and then we would have advection of continuously colder air from the south towards the north, and the Foehn effect is also diminished by this cold air advection from the south. So I put a 3-point. I'm not sure if there's not another reason for that, but this was the explanation that we found after some discussion on that topic. So much for that situation of the cold front that goes along the Alps. The fazit is that the model fields are very good, especially from EUMeTrain, and that all the things we see in the satellite image have their counterpart in the model cross sections. To finish the weather briefing, I want to show 2 images of recent cyclonic storms over India. I think you have all heard of that. These images are taken from ePort Pro. They are taken from Meteosat 8, so the first Meteosat of the 2nd generation that is now positioned over the Indian Ocean. You have the Severe Storm RGB here, and you see the landfall of cyclone Tauktae, but I'm not sure if the pronunciation is correct. You see a lot of humidity and convective cells and a lot of precipitation that will fall over land, but also wind speed was a matter and was really threatening this region of India. Unfortunately, a few days later, there was another cyclone, this time from the other side, from reaching the east coast of India, also having a typical cyclonic structure and making landfall, bringing again strong winds and massive amounts of precipitation. So if you the name of this cyclone was Yaas, but I'm again not sure if the pronunciation is correct. So if you want to have closer look at the images, you can use ePort Pro. This is taken directly as a screenshot from this tool. So, and to finish my part, I want to point out the next weather briefing that will be held on 22nd of June by the Finnish Meteorological Institute. And yeah, if there are any questions, or if you have another idea about why there is so much cold air advection over such a long period over the Alps, please post it in the chat box.